Hello and welcome to my master's thesis presentation. The topic of the thesis is ways of measuring outdoor lighting and mapping it using Geographic Information System (GIS) software. My name is Conny Arén and the supervisor of this thesis is senior lecturer Paolo Pinho and the advisor is doctoral candidate Dmitry Ingi. The contents of this presentation are a brief background why this topic is important. Then I present the research goal of the thesis, then the main findings of the literature review, which include the methods for measuring and mapping, the previous research in this topic, and some theory about vignetting. Then in the experimental part, there's camera calibration, data gathering, and vignetting analysis. And finally, what are the main results of the thesis? But first, a brief motivation why this topic is so important. Outdoor lighting is important for health and well-being of humans and for the safety and feeling of safety in dark conditions. However, too much lighting causes problems for human health, but also for animals, nature, and for sky glow and electricity consumption. For these reasons, it's important to measure and map outdoor lighting to detect areas of excess lighting and poor lighting quality. There were two main research goals of this thesis. The first one is to research and review existing methods for measuring and mapping outdoor lighting. And this should be done with particular focus on UAV-based imaging methods. The other goal, which is more for the experimental part, is to find out what is the significance and calibration process of vignetting. So the literature review reviewed different methods of measuring and mapping outdoor lighting. The measuring can be done with different instruments, for example professional equipment like luminance meters, but also digital cameras can be used, which are of course much more accessible. The reason digital cameras can be used is because the information in each pixel in the form of RGB values can be converted to luminance values and with a calibration constant give the precise luminance values for each pixel. Whichever measurement instrument is chosen, it can be attached to, for example, a tripod, to a vehicle, on ground or in air, for example, cars, or drones or satellites, planes. The method in focus for this thesis was camera-equipped drones, because the drone has high mobility and the camera can be used for many measurements in quick succession. And also drones don't have to abide by traffic laws and they don't have to follow traffic paths. They can just fly over buildings, fly over any obstruction. This method of camera-equipped drones has been used, for example, for measuring light pollution, for measuring the energy efficiency of outdoor lighting, and the lighting patterns during nighttime. There were also some techniques in different papers, like sky collimators and laser point clouds, that were used in combination with drone imaging to produce different types of data that could then be analyzed for different purposes. But vignetting was not considered in many articles, even though it is a potential error source that does indeed affect cameras. But a bit more about the vignetting. So it's a phenomenon of reduced light transmission at the edges of the camera lens. The reduction depends on the optical parameters of the camera and lens, and is affected by aperture, focal length, and zoom of the camera. The pictures on the right present some examples of a vignetting profile. They can be cylindrical, like the first one, where the reduced light transmission is only dependent on the distance to the center, regardless of direction. It can also have an offset to one side, like in the middle picture, where the highest value is not in the center, but slightly to one side. Or it could be like the last picture, where it's completely irregular and each corner has its own behavior. So that was the theoretical part of the thesis. Then I wanted to find out the vignetting effect through a practical approach. And for this I used a DJI Mavic 3E wide camera, which was calibrated with an adjustable calibrated integrating sphere as a light source. This calibration setup can be seen in the picture on the right. The pictures taken in the laboratory in the previously mentioned setup look like the picture on the top right, where it's a light source in the center of a picture with a dark background. This light source can be converted from RGB values to light intensity values with equation 1. Then from the light intensity we can calculate the calibration constant with the help of equation 2. For this, the average light intensity of an area of 100 by 100 pixels in the middle of the light source of the light intensity picture on the bottom right was used as the light intensity value. In equation 2, in addition to the luminance value of the integrated sphere, we also need the values of the camera settings in order to calculate the calibration constant Kc. Once we have calculated the calibration constant, this camera can then be used to measure luminance values of unknown light sources, because once the calibration constant is known and the settings remain the same, the only unknown is the luminance value. Then I calculated the vignetting correction function. This was done by taking many pictures in laboratory conditions, where I moved the light source within the field of view of the camera in between pictures. Here on the bottom are a few examples of the pictures. There were a total of about 30 pictures with the light source in different places. Then in MATLAB I extracted the luminance value of the light source and the coordinates in the pictures, and found that this drop in luminance magnitude follows a cylindrical pattern, which means that it's only dependent on the distance to center, which of course made the calculation quite a lot easier, and the vignetting function can be seen here on the right side. And then it was time to get the data gathering in outside dark conditions. This was done as late as the 29th April due to very late snow conditions on the target area of Otaniemi in Finland. At this time of the year, it doesn't get darker than astronomical twilight, which is still dark, but not as dark as it can get during winter. The conditions were also dry, very little wind and very little traffic that could disturb the measurements. I used two different settings with different drone speeds, shutter speeds and ISO, so that I could then compare and see if the vignetting also depend on the settings or if it changes with different settings. And the overlap that was used was 90%, just because then there's no harm in getting too many pictures, even though mapping usually uses much less overlap. After the data was gathered, it was time to do the vignetting analysis on this series of pictures. The purpose of this analysis was to find out if vignetting correction on points that are not in the center of the picture have a positive impact or not. So in this method, I chose points and measured their luminance magnitude in different pictures in the series. So in some of the pictures, or in one of the pictures, each point was quite close to the center, which gave its highest luminance value. And then in other pictures in the series, this point was further towards the edge, which means that it should have a lower luminance value based on the vignetting theory. And based on the results and findings of this method, this was indeed the case, and correcting the luminance values based on the distance to the center improved these values significantly using the vignetting correction function. So the results of the vignetting analysis included a lot of data points and tables, which would be very difficult to present in such a short format, but they suggest that vignetting correction has a positive impact on the luminance magnitude of points that are not close to the center or within 30% of the distance to the corner, which could be seen in the vignetting correction function obtained in the laboratory conditions. Based on this, in theory, the overlap could be decreased from a luminance magnitude standpoint, but when mosaicing and choosing an overlap, other factors have to be considered, like tie points, for example, which is outside the scope of this thesis. Another results was luminance images with absolute values, like in the top picture. These were possible to make due to all the calibrations and vignetting function that were already used for the vignetting analysis method. And finally, by comparing the settings of the two flights, they did not have an impact on the vignetting analysis, and by visual inspection, the quality is not far off. There is no significant increase in blur, for example, for the higher drone speed setting. The biggest difference is the different brightness, but this is due to the ISO value. So this suggests that higher drone speed is possible as long as the shutter speed is adjusted accordingly. Thank you for listening, and especially thank you to Paolo Pinho and Dimitri Ingi for the good advice and guidance throughout the thesis process.